Firstly, thank you for inviting me to your seminar series, and I'll just jump straight into the talk. So I think the first thing to address is there's a very long title. There are many keywords in there. One of the first keyword I would like to address is really what is efficient code. And by efficient code, I usually equate it to our traditional high performance computing code, right? You want to get as much out of the machine as possible. And by that, I mean, we want to use the machine as efficiently as possible. And we know that that's a very difficult task even for those who are experienced, it's also a very time consuming task. So what I show here is something we've seen many times. We've probably implemented it many times when we work in the area of HPC, which is matrix multiplication. So quick run through over the plot. On the horizontal axis, I have the different problem sizes. On the vertical axis, I have the performance in terms of gigaflops. Now, the important thing is that the top of the plot, indicated by the red line, is really the theoretical peak of the given machine, right? That's the best you can do under the ideal situation. And if we implement matrix multiply, we have the textbook implementation, our triply nested loop, that gives us maybe 2% of peak performance. If we spend some time optimizing it, then we get between 30–40% of peak, depending on how much time we want to put into it and how much effort we want to put it in. But if you look at an expert implementation, and by expert, I mean things that you probably could get with many of the vendor provided libraries, you're talking about an expert implementation that can get easily 80–90% of the theoretical peak performance, as indicated by the blue line you see here, right? The main thing here, what I want to say is that from the textbook implementation to the expert, there's usually more than 30 times improvement. The question is, how do we take the expert implementation and not just implement it on one architecture, but across many different architectures and on many different applications, which may not have experts implementations? And that's about efficiency. Really, when we talk, and I've highlighted that if efficient code is difficult, then how do we make portable code or portable performance easily accessible? And here I'm talking about portability across many different axes. Number one, time, right? Here we look at just CPU architectures. They have been evolving many times. Many new architectures are being introduced every couple of months, right? We've heard of Moore's law, and things are still evolving rapidly. And not do they just make the processors faster. Each new generation of processor typically gives us new capabilities. Previously, we do not have vector instructions. Then we have vector instructions. Now the vector instructions are getting longer, and the more recent architectures have even more complicated, more complex vector instructions, or SMT instructions, if that's something that you're familiar with. These vector instructions are more capable of doing more things now. So every new generation of CPU, we have more architectures, more capabilities, and they run faster. How do we get maximum use out of it? Beyond a single platform, today we have many different architectures. We no longer talk about CPUs, we talk about FPGAs, we talk about GPUs in a HPC domain. But beyond just CPUs and GPUs, we are starting to see more and more heterogeneous architectures. Architectures where you do not only have a CPU or a GPU, but usually you have multiple devices, multiple capabilities, all integrated into one single package. So how do we use them? How do we get good performance out of them? And lastly, like I mentioned, we have applications. Now, applications, as we get more and more capable computing devices, we have more and more new applications coming on board. And the best way to think about it is to look at machine learning, right? In the Turing Award speeches, you hear that the theory has been around for many years, but it's because architectures and computing platforms have become more and more powerful that's now feasible to actually compute to bring many of the theories into practice. And so this is as we get more and more architectures, more capable architectures that can compute more, we have more applications that we have not seen before, we have not thought of before. And these new domains, new applications do not have experts that would spend the time and effort that we traditionally would have spent to optimize them. So the question is, how do we get performance for all these new applications that may not have experts to actually tune them to get good performance? In short, what I'm saying is that performance portability, in this case, writing efficient code and making it portable, is really, really necessary, and is increasingly becoming more and more a challenge. Specifically, our traditional approach of manual optimization is no longer scalable. It has not been scalable, and that's why we have many tools that have been developed. But with the additional challenge of portability, it really goes out the door. It's no longer something we should manually try to optimize for each individual architecture, platform, and application. And the reason is simple, right? All the effort that you put into optimizing a code essentially has to be thrown away, and you restart from scratch if you're taking an optimization per device, per application approach. Today, we have many black box tools, such as auto-tuners, and we have expert libraries, assuming your domain has the benefit of an expert providing libraries to everybody in the community. But these black box tools and libraries, they give you good performance. They give you fast implementation, but the biggest problem with them is that they provide very little insights into why an application or an implementation is performing well or not well, right? And for us, I think that's the critical thing about the last part of the title, which is explainability, right? How do we gain insights from an implementation after we've done all the optimizations, after we've done all the job of making a piece of code as efficient as possible? What insights can we gain so that we can actually take that same insight and move it from one architecture to another, or even use them across not just architectures, but different domains? So my research group actually tries to answer two key questions. Number one, how do we capture knowledge about performance, right? Like I've mentioned, if we've optimized the code, how much of it can we reuse? How much of it we can retain for other application, other domain, other platforms? And that's the second question. How do we apply to different applications and different architectures? And our approach really boils down to the text scenario, and that is using analytical models to create explainable designs. So let me explain what I mean by analytical models. The key premise behind our approach towards analytical models is not about trying to capture or predict what's the performance of the architecture of a particular implementation. Specifically, what we want to do is to capture the hardware and software interactions that occur within an application. And the rationale is this. Very often, when we write code, high-performance code in a particular manner, in a particular fashion, we often write them in a way that targets specific hardware features. For example, we may write something that tries to use the functional units or computational units available as efficiently as possible. Or we may try to target different levels of the memory hierarchy. We often write code that targets specific hardware features. what my group is trying to do is actually to try and capture all these analytical models, to come up with analytical models that capture the interactions between the software and the hardware, right? And as the model change, as the hardware change, we know that, okay, based on the model, only certain parts of the software needs to be updated. So let me explain with the picture on the right. So here, what I have is a high performance matrix multiply, or a cartoon of the loop structures of a high performance matrix multiply. The important thing here is that the red box is where all the computation happens. And then the blue boxes around it are loops that are targeting the different levels of the memory hierarchy, right? So by splitting them into, these are the work that has to do with the computational units, and these are the loops that have to do with memory movement, we now can come up with multiple different models that says, okay, if something happens to deal with the functional unit, the computational unit, then only the red box needs to change. Otherwise, the other parameters, the other models that manage the data movement has to change as well. As such, this is what we try to capture. How do we this is what our analytical model is supposed to do, capture the hardware and the software interaction. And so that when we move to different platforms, we know exactly what needs to be changed. So what do I mean by hardware and software? Well, in order to use hardware, we know that a particular architecture platform, particular hardware must be fully utilized to get good performance. And here, I'm not saying whether it's computational unit or memory unit. We're just saying that if you have a piece of hardware, you want to use them as efficiently as possible. You want to use as much of it as possible, right? And you want to use them as smartly as possible. So for example, if you have computational units, you can characterize these computational units by a couple of key parameters. For example, how many functional units do you have? What are the capabilities of each functional units? And some of that capability includes how many outputs can you compute per functional unit? And how long does it take for each functional unit to compute the necessary output? Now, if you're familiar with instruction pipelining and things like that, then if you multiply the number of units, the number of outputs, and the latency or the time it takes to compute each output, then what you have is a formula that's given by this product below that says, hey, on any given architecture with, in this case, fuse multiply or FMA units, then when you multiply the number of outputs, the number of functional units, and the latency, this is the number of independent outputs that needs to be present in the workload in order to fully utilize the functional units. So if you're on a CPU, you may have maybe 2 functional units. We may have SIMD units with a particular latency. You multiply them out, they give you a particular value that represents how many independent instructions, outputs that needs to be computed. But if you're on a GPU, then you may now have much more functional units, but your latency may be shorter, or you may have the number of outputs per functional unit is smaller. So on different architectures, you have different numbers of units, functional units, different number of outputs computed, and different latency. But regardless of what architecture, they all have such capabilities. So now you now have a architecture agnostic formula that describes how many independent outputs needs to be computed in order to satisfy the hardware constraints of using the functional units as efficiently as possible. Now, that's the hardware constraints. Then what does it mean on the software side? Well, if you are doing matrix multiply, we know that there are 3 main parameters. the size M and N of the output indicated by the red box here, and the inner dimensions. In this case, I labeled it KC. Now, as we know, there are many ways of implementing matrix multiply, but regardless of which way you choose, in order to have many independent outputs, then the algorithm you have to choose is the one which does the matrix multiply as an outer product. Essentially, what I'm saying is that you need to take a column of A, multiply with a row of the B matrix in blue, and then you do an outer product of the two vectors, computing MR times NR outputs all at the same time in each iteration. And then in the next iterations, you need to multiply the next column of A and the next column of B, and you proceed accumulating different outputs, outer product outputs into the same output matrix. Now, why do I say that this is the algorithm you have to choose? Number one, if you look at every single iteration, each outer product, all outputs can be computed independently, in the sense that you don't need to wait for one output element to be completed before you compute the next element. So you have a lot of independent outputs that can be computed. As such, you know that in order to compute matrix multiply, then your two parameters, MR times NR, which is the size of the output, has to be greater or equals to the hardware constraint. If you have a matrix output where this equation inequality is not satisfied, then you know that you will not have enough independent outputs such that all your functional units, all your computation units are utilized fully. As such, you know that you're going to expect lower performance. Now, this is just one equation where you now type a software parameter, in this case, two software parameters, in this case, MR and NR, type two hardware constraints. Now, we can always add more, and we do have more, that ties what's the maximum size of the matrix that you can have to the number of registers you have available. We can tie but the key idea here is that for every analytical model, we can come up with an inequality that describes how software parameters is tied to particular hardware parameters. Right. So when we move to new hardware capabilities, for example, matrix engines or matrix multiply accelerators, these are something that are upcoming in many architectures that are announced this year. We can do the same thing. We can build a single model for a different that encompasses the range of matrix engines or matrix accelerator, and we can combine them and put them into a single model that can handle different architectures, matrix engines. And the interesting thing about matrix engines is that each matrix engine can handle different types as well. So we can also encompass the type information into the analytical model for matrix engines, and then we just specialize them as and when we get to an actual architecture. If you do it accordingly, and here we show performance plots for two architectures that we have used our new analytical model for matrix engine. And you see that for the most part, most gets between 70 to 80% of peak performance, right? In short, if you have a single model that captures the register, the functional unit, latency, throughput, and so on and so forth, then that same model can be used across different architectures, can be used across different implementations, and you have now captured knowledge about the expert knowledge about how optimizations done in the software is tied to particular hardware capabilities, right? Now, I've talked about matrix engines and functional units. They are all just on the computation side of it. Even for a problem like matrix multiply, and you see that the functional units are really just the small little red box at the bottom of the pyramid, right? That's where the functional units are. Most of the code in a high performance matrix multiply implementation is less on the computational side, but it's really about data orchestration. Now, here, the important thing to note is I said data orchestration and not data movement. And because to us, data orchestration is a more generic term, a larger term than just data movement. And while the key idea is to keep the functional units as busy, remember we want the functional units are the things that are actually doing the actual computation that we are interested in. Data orchestration is about moving the data as efficiently as possible from main memory or wherever it resides. It could be distributed, could be on this, through the different layers of memory into the register so that the functional units can compute with them, right? So yes, data movement, as I've mentioned, is very important. But a second, and in some sense, a more important task is about managing the caches, managing what data sits in which level of the memory hierarchy. Can I keep a particular portion of my matrix in the L1 cache for as long as possible? Can I keep a portion of the data in L2 as long as possible, right? And this is not just, the question about where to put the data, how to put the data, how to manage the cache so that the data you want kept in a particular level is not kicked out is really part and parcel of this whole data orchestration discussion. So remember, one of the key things about data orchestration is making sure that the data reaches the functional unit just in time. And for this, we use double buffering very liberally. And I use the word double buffering, even though we may not often create a secondary buffer. Essentially, the whole idea about double buffering, and I put that in inverted quotes, is about how do we bring in data ahead of time, issue the loads and store loads early enough such that there is sufficient time for the data to percolate through the memory hierarchy into the register so that we can compute with them. And so the amount of buffering and how we go about doing the buffering really depends on where's the data. By saying where's the data is it in L1, is it in L2, or is it in main memory, right? How much data is required for us to bring the data in? Are we just bringing a single element, or are we bringing cache lines worth of data? And once we bring in the data, how much time do we have? Now, clearly the amount of computation time that we have must be less than the time we need to bring the data from different levels of the memory hierarchy. And this is where a trade-off decision has to be made, right? If we want data to be in L1, then we can afford to have, we only need a small amount of computation time to hide the cost of bringing the data ahead of time. So maybe even double buffering, if the data is in L1, is not necessary. But as you go lower and lower down the memory hierarchy, further and further away from the functional units, then the latency increases. Then we need to find places where we have sufficient computation time, or we need to bring in more data much earlier. So this trade-off can be described, but it really depends on what's the computation that we are trying to perform. But the general principle remains the same. As long as we can hide the cost of bringing the data, we want to bring the data in as early as possible. And you see from the performance plot that the difference between buffering and non-buffering. And here, what by buffering, we are just bringing data from L2 into the registers. What you see here is that if you perform matrix-matrix multiply where one of the matrices sits in L2, and if you do not perform buffering, you see a significant difference between buffering and non-buffering. So the gray line is the non-buffering approach. The red line is the one with double buffering, right? So it's essentially what we are saying is that you have to do double buffering as liberally as possible, but that amount of buffering that you need really depends on where the data sits at different time of the memory hierarchy, at different time of the computation, and at different levels of the memory hierarchy. So I've said that we need to keep data in the memory hierarchy many, many times. So how do we keep data in the memory hierarchy? And to do that, we want to model different data layouts in the caches. So when we talk about caches and modeling caches, usually things like the size of the cache line size are all very common parameters. And the software parameters that we are interested in is really the blocking or tiling size. However, it turns out that beyond the size of the cache, the associativity of the cache matters significantly as well. So let me illustrate again with matrix-matrix multiply. So on the top here, we have our matrix-matrix multiply parameterized by 3 parameters, MR, NR, and KC. And if you are on in this case, an 8-way set associative cache that we show on the bottom left, you need to split up the 8 different ways amongst the 3 matrices. The output C, A, which is the green, and blue. Now, MR and NR, based on the functional units, we will have some values that we have came up with that satisfies the hardware requirements in terms of the computational units. So we do know what MR and NR is. But now what we need to find out is what's the size of KC? How do we keep a particular matrix, in this case, let's say the blue matrix, in cache? Right. So here I showed 2 equations. Essentially what we are saying is that, all right, because I have 3 matrices, I have to clearly partition my 3 matrices across the 8 ways available in the cache. Now, I know my output is MR and NR, and I have no idea where the starting address is. So I have to allocate an entire way to fit my output matrix, right? Because I don't know what's the starting address. It potentially may cover any possible range, but I know that given my set, if I leave one entire way available in my cache, then I know the starting address will fit somewhere within that way in the cache. Now, this accounts for one of the 8 ways I have available. Then I just need to split the 2 matrices, A and B, or green and blue, within the 7 ways left. Now, and that's what this formula is trying to say, is simply saying, hey, just split them so that you fill up the caches as much as possible. And once you figure it out, then the values of KC can be predicted based on the associativity of the cache. Now, so what happens if we move to a different level? Well, the same thing happens, right? Now, on the new architecture, instead of 8 ways, maybe we have 4 ways worth of cache. Again, I leave 1 way for C. This leaves me 3 ways. And then I'll split the remaining three ways between A and B. Now, notice that in this new way of splitting the data or splitting the cache, one specific way is left completely empty. Effectively, what we are doing is we are giving up 1/4 of the cache by not filling in data. But it turns out that even though we are not using the cache as efficiently in terms of percentage of data packed, in terms of performance, because we are managing the cache very efficiently, we often get better performance than if we were just to fill up the cache completely. If you fill up the cache completely, as close to 100% of the capacity of the cache, what often happens is you end up incurring a lot of conflict misses and forced eviction. And this avoids this, as a result, kicks certain particular cache lines that you may want out of the cache, and therefore diminishes performance. As such, by carefully organizing the data such that we organize them nicely, making sure that there's enough way for data to go through the different levels of the memory hierarchy, we reduce the number of cache conflicts, cache evictions, even though we may not utilize the cache as effectively as possible. But overall, we get better performance by modeling how the data is moved in and out of the different levels of the memory hierarchy. Now, in order to do that, what we really need to do is to actually introduce the notion of intermediate layouts. Intermediate layouts are not layouts that are exposed to the end users. Effectively, users pass in the default layout, and default depends on what application and what domain you're using it. But within the computation of either a matrix multiply or FFTs or any computation you want to do, what we end up doing is we repack the data. As we move the data through the memory hierarchy, we not only move them we are not only just reading them. What we do is we often read them, pack them into a specialized buffer in a particular data layout so that we get streaming accesses, so we get good cache locality. And we have the good property that by packing them, we know what's the starting address, so we can predict with good accuracy how the cache will be used in spite of the uncertainty about which cache line will be kicked out. So once we pack the data, we now have some sort of guarantee that, okay, this will fit nicely within, say, 2 ways of the cache. When I bring in the next data, I have enough space within each set to bring in new data that may be required by other layers of the memory hierarchy, or to actually kick data out so that I can keep certain levels, certain piece of information in a particular level of cache, be it L1 or L2. We have some guarantee of where they are, right? And so in the past, we've not just done it for matrix multiply, but we've done it for FFTs and direct convolution, and they all use the same idea of this intermediate layout where we change the data layout that is unexposed to the end user, but it gives us good predictability and good cache locality so that we can move the data more efficiently. So I've talked about matrix multiply a lot. The question is, how general is the approach? Is it only restricted to matrix multiply? And again, one of the questions that we are interested is, can the models be used across different applications, across different application domains, right? Or are they just one and done kind of approach? And the short answer is no, they're not one and done. And to demonstrate that, we talk about fast Fourier transform, or FFTs, right? FFTs are usually considered memory bound. They are memory bound operations because they have low arithmetic intensity units. But if the data is at the right level of the memory hierarchy, in the right level of cache, what you see from the two plots on the top is that they are often fast enough, if they are in that particular level of the memory hierarchy, to actually reach near the floating point addition peak performance, the theoretical peak of a floating point addition unit. So for example, on a Haswell, it has one floating point SIMD unit with a throughput of 1, so you can compute 4 floats per cycle. And you see, if you use all the different things like different layouts and putting in the right levels of the memory hierarchy, you see that you can get close to 4 floating point additions every cycle. And similarly for the KB Lake, you can get 7 out of the 8 floating point additions every cycle. So FFTs, if they're in the correct level of the memory hierarchy, the caches, the memory systems are fast enough to actually make sure that you get close to peak performance. Now, here peak is not your fuse multiply add, but is addition, because a lot of the computations within an FFT are usually additions and subtractions instead of fuse multiply add. But nonetheless, what we are showing is that, hey, if you know where the data is, then you can predict how fast can the memory, how good are you using your functional units. Now, in order to make sure that the data is in the cache, then what we did, not surprising, is to do double buffering. So we, instead of using all our threads to do computation, what we did was we use a thread. You use half of the threads to actually read data from main memory into the caches, and then the other half of the threads to actually compute on the data that's already in cache. And we know that it's in cache because we've loaded it with the other set of threads. And on the bottom left, what you see is the performance for it compared to MKL and FFTW on Intel KB Lake. We often get a significant boost with the double buffering approach, where we use one thread to bring in the data and then the other thread to do computation. And we know that with one thread, it's sufficient to do computation, is because, again, if you look at the top two plots, with one thread, the caches are fast enough to actually sustain the rate of computation. So we actually don't need to use more than one thread for computation. And once we move things into the caches, not surprisingly, we get the opportunity to change the data layout at different stages of the computation. And we do actually see that we need to change the data layout at different stages. So how do we do buffering instead of into the cache, where we often do not have control over the cache replacement policy? Well, the key idea is, number one, instead of just randomly assigning half the threads to perform double buffering, half the threads to do computation, we specifically allocated threads such that the two threads allocated on a single core, one is performing double buffering, one is performing the computation itself. This ensures that even though the threads may not have, this ensures that, within a double buffering thread and a computation thread, because they share the same cache, they said, then there's a high likelihood that the cache, the double buffering threads will load the data into the appropriate levels of the memory hierarchy for the computation thread, especially since on many x86 architectures, each different cores have different private caches. Now, to do the data movement across different memories, layers of the memory hierarchy, what we had to do was to use additional instructions like the temporal loads and stores, so not your regular load and stores. We need to have logs for correctness. But the important thing is that, again, you see that because the cache is used for different purposes, right? One for computation, one for double buffering, one for the outputs. We now have to split the caches carefully to different ways such that each thread is allocated particular ways of the cache, not sets, but ways of the cache, such that we know that they do not trample on each other and kick each other's out, kick each other's data out of the cache. So the double buffering cache, the double buffering thread has specifically sized and organized data so that we have the high guarantee that the double buffering thread do not kick out the data it has previously loaded and now is being consumed by the computational thread, right? And because the threads are on the same core, they share the same functional units, and both of them are doing loads and stores. Clearly, for the double buffering threads, they have to do loads and stores. But even for the computational thread, they have to do load and store to even load the data to begin computation. And now you have a contention on the load and store units, not computational, but the load and store unit. And what we had to do then is to introduce no ops within the double buffering threads so that there's a pause in the computation so that the other threads can proceed. So this is a case where, yeah, the model tells us that, hey, all the functional units, in this case, the load store units, are utilized completely. We actually need to introduce no ops to actually improve performance. If without the no ops, then the performance of the overall approach looks as if they were done completely sequentially. Right. I've talked about FFTs, but really many problems are matrix multiply in nature. And many of these problems that look like matrix multiply are applications in newer domains like computational biology, machine learning, graph algorithms. Many of them can effectively be written, can be written with a triply nested row. It may not be efficient, but you can write them that way. But since they can be written as matrix multiply, then a lot of the models that we have can be reused. For example, in population genomics, instead of doing the latency and throughput of the fuse multiply add or FMA units, what we can do is replace them with the latency and bottleneck of the pop count units, which happens to be the bottleneck on the population genomics architecture. So you can actually predict based on which the instruction is the bottleneck, what is the model you should be using. And once you see the model, then it's a matter of just going through the model, filling in the parameters and propagating the information throughout. And if you do that, again, you can get 80 to 90% of the peak performance of, in this case, the pop count units for the population genomics. And you can do similar things for k-nearest neighbors and many of the matrix multiply application itself. Now, in machine learning, what we are looking at and we have been looking for a while is to cast things in terms of direct convolutions instead of matrix multiply. The traditional approach is to take your data, repack it into a separate buffer, usually called the im2co process or lowering process. And this packing is usually done either explicitly, as in you copy it into buffer, or implicitly as part of your cost to matrix multiply. Our approach towards machine learning is to actually just to do direct convolution directly without this additional buffer overhead. And again, using the analytical model, using the for both the computation and the memory hierarchy, and reshaping the loop so that they actually correspond to the hardware features, then what we show is that, yes, you can actually get a convolution layer using the direct convolution algorithm without using the additional memory that is required for machine learning. So in other words, the analytical model gave us a different way of doing convolutions without the additional memory or the need to cast it into matrix multiply, right? And we get good performance and things like that. I'm not going to go too much into it. Modeling, it extends not just to a single node, but we have work that demonstrates how we can use a modeling approach and extend the FFT algorithms to larger machines like the exascale machines that we see today. And the whole idea is, how do we come up with new ways of moving data, in this case, across multiple nodes instead of across different memories hierarchy, and what is the new layout that we require to get better performance. And we get strong scaling to more nodes with our new implementation. More recently, what we have looking at is to move towards the irregular domains, the graph and sparse linear algebra domain. So we are very actively involved in the Graph Blast community on how do we use sparse linear algebra to compute graph algorithms. And one of the things that we are working on right now is to use our modeling approach to find out what are the different hardware bottlenecks for different graph algorithms. Very often people say that it's a memory bound problem, but before we reach the bandwidth limit, are there any other hardware limitations in between? And so that's something that we're actively working on right now. So in summary, our approach towards portability and performance is to really build analytical models. And these analytical models are designed to capture key software and hardware interactions. They are not specific to any architectures. They're not specific to any applications. They tell us what must be satisfied in order to use the hardware as effectively and efficiently as possible. And because we do not capture specifically domains, then we get to pick and choose which model to use for different domains, for different applications, for different architectures. And that gives us the flexibility and portability across both architectures and application domain. The interesting thing about analytical models is also it forces us to rethink many of our current algorithms and implementations, right? Based on the new hardware capabilities, what can we do with our existing algorithms? And I don't have time to go into much detail about it, but the interesting thing is a lot of we get to try out new algorithms because now we understand what the hardware can do and what we can play with on the software side. And of course, once you have an analytical model, then it makes it very easy to integrate into tools such as Poly, LLVM, and so on and so forth, right? And the analytical for models for matrix multiply has already been integrated into Poly, thanks to the people at Poly. And now not only does it solve the matrix multiply problem, but with Poly, you can now target many other domains that an expert developer would never have time to. So for Poly, if you use the tool, now you can use it for many other applications that can be written as a triply nested loop with different functional units or computation that needs to be performed. So the analytical model, once integrated into existing tools, definitely increase programmer productivity, and it gives us portability and performance. Well, with that, I come to the end of my talk. Are there any questions?
Thanks a lot to Meng for this interesting talk. Are there any comments or questions? Dominic?
Yeah, thank you for your talk. It's very interesting because I'm also researching in performance prediction for code generation. What I still I'm not sure about is so you have a performance model, for example, for matrix multiplication. If you move to a different application, what do you adapt, or what is it that you change to account for the different application?
So I would claim that I do not have a matrix multiply model. I have a model that says what needs to be satisfied in order to use the hardware as effectively as possible. So I have a model for the computational units. I have models for how you want to use your cache. I have models for how you want to use your registers and so on and so forth. Right. So if you happen to move to a problem that looks like matrix multiply, then it's a matter of figuring out, instead of the fuse multiply add, what functional units is your bottleneck unit. And one example is the linkage equilibrium or population genomic problem, where it is effectively a matrix multiply, but you're not dealing with real numbers. What you're dealing with is binary matrices, ones and zeros only. And if you analyze the implementation, it turns out that the bottleneck instruction happens to be the population count. So you use the same model, but you use the latency and throughput of the population count unit instead of the fuse multiply add unit. So for that operation, because it's so similar, you change only the you use the model, but you replace it with the correct numbers. So that's what you do. But for the caches, for example, we talk about the FFTs, and we use the FFTs. We did not use the matrix multiply the functional units model, but we used the cache model to split the data between different to split the caches so that different threads can access the data without trampling on each other. So it depends on what's your application, you pick and choose what model you want to use. So that's why I say I do not have a single model for I pick and choose to achieve what I want to do. Remember, our models are meant to capture the optimization required to use the hardware as efficiently as possible. So it depends on how you want to use the hardware.
So in the first case, with the genomics, you parameterize the matrix multiplication model to do different things. So that would require that another application has a bit like a similar structure, like the 3-loop structure. And for other applications, you take the building blocks and build a different performance model.
Right. So think of them as building toy blocks that you can piece together for individual domains. So they are one level lower than actual applications.
Okay, but that's a bit of a manual process. So as a programmer that targets a new application, I have to look at the application, and then I pick and then I craft a new model that fits for this application.
And so that's why the work by the Poly folks was very interesting, because we didn't implement the model. They actually took our model and integrated into Poly. So and I think that's the important thing, right? We are HPC folks. We know how all the nitty-gritties about how hardware and software needs to be put together. We are not in the compiler or productivity domain in that sense. But working with them, they take our models and now they make it more widely available. So what that particular module in Poly do is that they analyze the loops. They recognize that, oh, by rearranging some of this, it's actually a triply nested loop. So the developer may not realize that they have written matrix multiply, but the tool itself, through its analysis, figured that out. and then they replace everything with the expert implementation, and then use our models to actually predict what's the parameters and so on and so forth. So there's a way forward, and it's not just my group, but there are many collaborations that can happen to actually automate many of these to make it more widely available.
Okay, yeah, thank you.
All right, thank you for the question.
Yeah.
Okay. Hi, thanks a lot for your talk. This is very interesting work. I also like the work about using SMT to prefetch data. So I remember we tried that years ago, but our experience was that the hardware prefetchers are much better. And very often you interfere with such techniques with the hardware prefetchers. So did you switch off hardware prefetchers? Because usually if you have linear access, your prefetching thread will not help.
Right. So if I recall correctly, since it's a bit of the hardware prefetcher is still available. So the reason I believe why we were successful is because when we prefetch the data, we actually we were not reading it. Sorry, we were reading it stream-wise, but once it's brought into cache, we actually reorganize the data.
But this reorganization is done by the prefetching thread.
It's done by the prefetching thread.
But maybe there's a different reason for your speed up, not the prefetching, because when you reorganize the data, you have a lot of shuffles and broadcast instructions. And now these instructions may, with the second thread, overlap with load stores and FMAs from the other thread.
That's what we did. The prefetching was to avoid the shuffles and broadcasts as much as possible. So we computed what they need to be so that we avoided the shuffles once they reach the registers. But
the prefetcher needs to do this. The prefetch thread needs to do these shuffles.
Right. It does have to. It does have to do it. But not the broadcast. Some of the shuffles you still have to incur because of the thing, but not the broadcast.
My interpretation is that your SMT thread doing the prefetching now does the shuffles while the other thread does FMAs or arithmetics. And now those instructions may go to different pipelines. If you have them in the same thread, they may have addressed these bottlenecks separately. Now they can overlap. Maybe did you check for that?
Oh, we definitely did. And the code we had, the computational side, there's still shuffles and computation that is happening. The implementation we did try to minimize the number of shuffles we do because we want to hit the computational peak that I've mentioned, even for the FFTs. It definitely is a matter of bringing the data in fast enough, because remember, if you're just reading directly from main memory, it is actually not fast enough to actually feed the functional unit. So we really need the double buffering to happen into cache first. Once it's in cache, then we can hit the peak compute capability. So the double buffering, and that's how we actually figure out that double buffering is important, because by not inserting the no op, everything looks sequential, and we had terrible performance. It's like, in theory, it should work. But once we figure out that, oh, the load store units were being hammered so heavily, and we inserted no ops in the, then both threads can run concurrently.
How do you make sure that your I call it scouting thread, your prefetching thread, doesn't run too far ahead? Do you synchronize the two threads at some point?
We synchronize the two threads. So in this implementation, it really is a double buffering, right? We allocated and designed the buffer specifically so that it fits the cache nicely with the outputs and so on and so forth. And then we synchronize so that we swap them accordingly, so it doesn't run too far ahead. Okay. So it's not like a real prefetcher. It's just prefetch. It's more of a double buffering thread than a prefetching thread.
Okay, thanks a lot.
I have a question which which is probably connected to that. You do a lot of modeling concerning how much or how large must things be to fit into certain other things. So volume modeling, let's call it like that. Mm-hmm. But what I'm probably missed is data transfer time modeling. Do you have any concept of how long it takes to get the data from A and B so that you can make the, informed decisions?
So we do, and it's so. For example, we know that one piece of data, say from L1 or L2, takes X number of cycles, right? And the X depends on the different architectures. And we actually look at our computational kernel, and we say, okay, with this size of the kernel, I have so much time available, compute time, based on the throughput and latency. And if I need to bring so much data, this volume of data from, say, L1 or L2, how long would it take? And then that helps us predict how much double buffering should I need. And this is not only at the L1 and L2 level, but all the way to main memory. If I say, if I'm on a GPU, I want to bring data from main memory, I need to do double buffering. So how much time do I have to bring in the double buffering? Can I hide it within the computation time? So yes, but it's a pretty simple equation. That's why I didn't present it.
Okay.
But yes, we do consider the time it takes to bring in data from different levels of the memory hierarchy. And that's why predicting and ensuring that the data we want is at the correct location is very important. And that's why I spend more time on talking about how to keep data at particular levels of the memory hierarchy.
Okay, thanks. Are there any more questions or comments from the audience? Doesn't seem to be the case. Then thank you again, Meng, for giving us this great talk. Thanks for taking the time so early in the morning, and goodbye, everyone.
Right. If there's any questions, feel free to reach out to me. That's my email below. I'll be happy to discuss more. Right. Thank you.